Hi everybody, we are in chapter 9 talking about differential equations. So our interaction with differential equations is going to be fairly minimal. We're only doing 3 sections in this chapter, but this is really a good kind of preview if you end up taking a differential equations course later on in your mathematics career, even here at SCC. But let's go ahead and just get started and introduce what is a differential equation. So a differential equation is an equation that contains an unknown function and one or more of its derivatives. So basically, a differential equation is an equation that has a derivative in it. Okay, so not anything too outlandish there for a calculus class. So we say that the order of a differential equation is the order of the highest derivative that occurs in the equation. So basically whatever the highest derivative is. So if it's a first derivative, then it's a first order differential equation. If it's a second or third derivative, right, we say it's a second order differential equation, third order differential equation. Here for our purposes, we're only working with first order differential equations. We then say that a function f is called a solution of a differential equation if the equation is satisfied when the function and its derivatives are substituted into the equation. To solve a differential equation is to find all its possible solutions. So the solution of the differential equation is any function that satisfies that relationship. Okay, so we have dealt with functions like this before in a much more simple context. So if we have the differential equation y prime equals x cubed, this is a first order differential equation. The general solution to this would be y equals 1/4 x to the 4th plus c. Okay, that would be our solution to this differential equation. Okay, because this function here satisfies that relationship. Right? If we took this function y and substituted it in there to y prime, you would find that it equals x cubed. Okay? So let's look at this example here. So show that every member of the family of functions given here is a solution to this differential equation. Okay, so the first thing I want to do is I want to look at y prime. I want to find actually what the derivative is of this function. So that's what we're going to do first. Okay, so to do this, we're going to need to employ the quotient rule. So that's going to be low d high minus high d low over low squared Okay, simplify that numerator, so that gives us c e to the t minus c squared e to the 2t plus, because again we have a minus here and a negative here, so it's going to be plus c e to the t plus c squared e to the 2t all over that denominator. Okay, and I wouldn't multiply out the denominator, it's just going to give yourself more work unnecessarily. Okay, notice we have a little bit of cancellation. We have a plus this term minus this term. So what we have left is 2ce to the t over 1 minus ce to the t squared. Okay, so that's y prime. So that gives us the left-hand side. Okay, so this is left-hand side of our differential equation right there. Okay. So now let's look at the right-hand side. So let's substitute our function right here into the right-hand side. So into the value for y. So I'm going to do that top of the next page. I left some more blank space up there for you guys. Okay, so let's substitute this in. So we have 1/2 y squared minus 1. If we substitute in this function, we get 1/2 1 plus c e to the t over 1 minus c e to the t squared minus 1. Okay, and then that is equal to, so 1/2. I want to give these a common denominator, so this one's going to have 1 plus c e to the t squared over 1 minus c e to the t squared minus, I'm going to give them the common denominator, so it's going to be over 1 minus c e to the t squared, and then multiply the top by that as well. And it was just 1, so we just get the same thing on top and bottom. Okay. So we do our squaring and apply that negative. So we go 1/2. We have 1 plus 2c e to the t plus c squared e to the 2t, and then minus, so everything here is going to get a minus distributed to it, so 1, then it would be minus 2c e to the t, so it becomes plus 2c e to the t, and then it would be plus, but it becomes minus c squared e to the 2t, and that's all over that common denominator of 1 minus c e to the t squared. Cancel where we can, so the 1's cancel, the square terms cancel. So what we have left, we have 1/2 times 4c e to the t over 1 minus c e to the t squared. There's a factor of 2 in that 4, so that leaves us with 2c e to the t over 1 minus c e to the t squared, and that's our right-hand side. And notice, if we go back and compare, right, the thing we got for the left-hand side, 2c e to the t over 1 minus c e to the t squared, that's exactly the same as the right-hand side. Okay, so this function does satisfy the relationship stated in the differential equation. So we can then conclude, so we'll say, therefore, for every value of c, the given function is a solution to the differential equation. All right. Now, this is just solving a general differential equation. However, we can also solve differential equations that satisfy initial conditions. So we've seen this a little bit in solving equations, but it works for differential equations as well. So solving a differential equation that needs to satisfy an initial condition is called an initial value problem. So we have an initial value problem. So along the same lines as our previous example, find a solution of the differential equation y prime equals 1/2 y squared minus 1 that satisfies the initial condition y of 0 equals 2. So in this case, we're going to substitute. So the t value is 0 and the y value is 2. And we already found the general solution, right? So we had y equals 1 plus c e to the t over 1 minus c e to the t. So substitute in our values, we get 2 equals 1 plus c e to the 0 over 1 minus c e to the 0. E to the 0 is 1. Okay, so that's a 1. That's a 1. So all we have left is 2 equals 1 plus c over 1 minus c. And solve for c. So multiply across, so we get 2 minus 2c equals 1 plus c. That's going to give us 3c equals 1. So c equals 1/3. So our solution for y, so y equals 1 plus 1/3 e to the t over 1 minus 1/3 e to the t. But we also like writing this without fractions inside a fraction, so you can multiply top and bottom by 3. This gives us 3 plus e to the t over 3 minus e to the t. And so the solution we found earlier was our general solution for any member of that family of functions. Here we said I want the specific one that goes through